Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Kalina from Business Review, and I will be your host today. It is our pleasure to have Ingersoll Machine Tools Incorporated with us today, who will be presenting this webinar titled, Can We 3D Print This Instead? Picking the Low-Hanging Fruit of Large Format Additive Manufacturing. Today's guest speaker is Curtis Gofinski, Principal Technologist at Ingersoll Machine Tools. I would like to welcome you to our webinar platform on 24. You will notice that this webinar is browser-based, so if you disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask any questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. We will allocate some time at the end of this session to address any questions or thoughts that you may have. Please use the yellow help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you in order to get a better view of the slides. But now please allow me to welcome Curtis. Curtis, over to you now.
Hello, everyone. Good morning or good afternoon. Welcome to our presentation titled, Can We 3D Print This Instead? 3D printing is a broad topic, so I'll start by introducing which additive manufacturing technology we're discussing. In this case, particularly large-scale 3D printing. And this presentation is focusing on the aerospace and defense, energy and transportation sectors, and other heavy manufacturing industries. The root question, can we? With that, a manufacturing engineer is really being asked, does it make sense to 3D print this? Is there a net advantage? And they're being asked to answer by evaluating factors like cost, lead time, quality, and risk. The final piece of the question, instead, implies a final important factor. How does the additive alternative stack up to traditional manufacturing methods? I'll use this presentation to walk through some of the AM process, introducing in particular the Ingersoll MasterPrint systems, which are large format additive systems, and then walk through determining some ideal applications for large format additive and analyze some example parts. So to start, we'll introduce Ingersoll Machine Tools. We're located just outside of O'Hare, just outside of Chicago, Illinois, in the United States. This is our main campus with a additive development center shown up top, but long-standing production contract manufacturing centers, assembly for new machines and new equipment, engineering, corporate headquarters, all under one campus with some additional upcoming plant expansion. Traditionally, we have over a century of machining expertise. Here are some examples of our in-house contract manufacturing. These are the size machines we're talking about when Ingersoll thinks large format additive. Using these platforms, these large machines, anywhere between 6 to 10 plus meters between gantry columns. You see the size of some of the machine operators there. And traditionally operating in the aerospace sector, mold making, aerostructures. In box 3, we see some traditional components of our own machinery that we are making on our contract capacity. And in slide 4, supporting the wind energy industries. We are also experts in composite manufacturing equipment, composite fabrication for aerostructures. On the left, we see a vertical format fiber replacement machine. On the right, we see a horizontal fiber replacement machine. These are laminating or laying up different layers or plies of composite material to make structures. An example of a composite machine that takes all of our technologies under one gantry or one roof is shown on the screen here, where we have automated fiber placement tape laying, trim, and ply inspection or composite structure inspection systems, all modular, able to be picked up by the same gantry. In this case, the world's largest composite manufacturing gantry, 9 meters between columns, additional travel outside of the columns, and 4 meters of Z-axis travel. This same modular format where we're taking multiple technologies to a single positioner can be taken to a robotic platform, and we have recently at the Connecticut Center for Advanced Technology to perform multiple manufacturing processes under the same platform. In addition to the metal cutting and composites manufacturing capacities, we've also started a venture into 3D printing. Around 2016, we started a partnership with Oak Ridge National Lab, and now every day these case studies that we're going to get to, these additive manufacturing processes, are being developed in our development center in Rockford, Illinois, where we've built a MasterPrint gantry for our own product development purposes. These parts look like pellet-fed single screw extruder. The parts are built in layers by multiple beads. So you see in the center picture multiple layers of a 3D printed part sliced, and on the right you see individual beads laid down of extruded plastic. So it's pelletized thermoplastics fed to a screw extruder. The extruder melts the plastic. For stability and strength, the plastic pellets are often pre-mixed with a chopped fiber reinforcement. It can be carbon fiber, glass fiber, biofill like wood, flour, flax, bamboo. So this additional capacity of 3D printing has been added. This is an example of our development center machine in Rockford. And we are also adding a even larger machine at Inse Milano in Milan to develop the processes and advance the feasibility of these applications in support of the European market, European aerospace and defense industries. This is our machine in Rockford. Very often, and because the large, say low resolution but high bead size of large format 3D printing, we not only have a printing module attached to the machine, but also a 5-axis machining head, traditional machining spindle unit. So our machines are fairly modular in size, expandable along their length, multiple interchangeable modules, and support an open material platform ranging anywhere from on low temperature ABS and PLA to high temperature PEI, PESU applications, and again, often filled with some reinforcement for strength and stability. We also have continuous filament 3D printing. I won't touch on these applications here, but this is more leveraging our experience from composite layup, from toe and tape layup, to drive a continuous filament as we print on top of parts or other more free-form contours. Here you see an up close of printing on top of a printed tool, printing out of plane, or reinforcing existing parts. And this is happening as Ingersoll is part of the larger COMPOSITE group in the manufacturing division. In the machine tool division, with the manufacturing division in Inse Milano receiving a MasterPrint machine to support Europe. I'd like to step through quickly the AM process and what it takes to run a manufacturing job for additive manufacturing. We start with design for additive manufacturing, where the manufacturing or the design engineer, as in traditional manufacturing processes, does best with some experience with the additive manufacturing process itself. So the design engineer is very much aware of what the machine is capable of, what the materials are capable of. Basically, the entire feasibility is best addressed at the onset, at the design of the part. The path planning or the CAM of CAD-CAM in additive manufacturing's case is more generally described as slicing, where we are actually planning the machine motion that is used to print the part. That machine motion then is translated into G-code, preferably also simulated to confirm the motion is safe, reliable, and making a good part. And this is also generally referred to as post-processing, where the CAM source code is processed into the actual G code or the NC code to go to the machine on the shop floor. In parallel to planning the path and sort of closing the loop with design for additive manufacturing on the shop floor, we have to develop the process parameters for a specific geometry, for a specific size bead that we are printing, or for a new material. And finally, actually quite far down the line, we get to print something. So the print is in production, the machine is running continuously and needs to be reliable, and also we prefer to be collecting information from the machine about the process parameters and the quality of the print. As I said before, usually we are post-processing or in some way finishing the surface or the important mating features or pieces of the print that need to be dimensionally accurate. This is why our machines incorporate a 5-axis milling head. And finally, closing the loop with quality assurance, being able to collect that data and then inspect the final part and compare and contrast, analyze how the processing parameters are affecting the final part quality. So we'll talk now about some ideal applications, or what makes up an ideal application, and how we judge exactly why or if we should print a certain piece when we're asked. So additive manufacturing as a technology is still maturing. Additive manufacturing in the factory is an even younger subsegment. And then again, large format additive manufacturing for industry is younger still. And because of this, I think it's helpful to apply the Gardner hype curve, which charts the expectations or quote unquote hype of an emerging technology over time from sort of a big bang disruption through the technology's maturity. I'd like to ask everybody, the audience, where we believe we are with additive manufacturing on this hype curve, from tech trigger to an inflated expectations, through a trough of disillusionment, climbing out of it with some enlightenment towards stable productivity.
Thank you very much, Curtis. Yes, right now it is time for the first poll that will be running in today's session. As Curtis already mentioned, today's poll question and answers to it are: where is AM on the hype curve, tech trigger, inflated expectations, disillusioned, enlightenment, or stable productivity? While the audience is voting, Curtis, if I may ask, what results are you expecting on that one?
I am expecting the results actually to describe the audience. So depending on your answer, I'm expecting either more or less experience, or say more or less heartache or heartbreak in your past with additive manufacturing.
Thank you. Let's see the results. 13% of the audience members have voted tech trigger. 30.4% have voted inflated expectations. Another 13% have voted disillusioned. 39.1% enlightenment. And 4.3% stable productivity.
Great. Thank everybody for your input. I think it shows that in most people's opinion, we are past our trigger of technology, or possibly some of those answers are even believing that we are very, very early on in the potential of the technology maturity. And then a large group under enlightenment is maybe showing that a lot of the audience has some experience with that heartache, where they have met the trough of disillusionment and seen some parts fail and some applications not be the right fit. I'd like to describe the hype curve in a little bit more detail from my own perspective, how I analyze where we are on the hype curve with this asymptote towards ideal adoption of a technology being exactly that. The plateau of productivity is the ideal adoption. It's where the expectations are matching with what the technology is capable of. And these two areas here, it's not that we want to be at the high peak, and it's not that it's bad to be at the low trough. It's actually that these two positions on the curve are fairly far from the ideal tech adoption, and that's what's bad about both of them. Above that, at the peak, we are wasting resources with too high of visibility and expectations than the technology is capable of, and underneath exactly that, an opportunity cost of unrealized potential. And I would actually like to say that heavy industry is maybe more of an overdamped curve, where there is a much longer time to adoption of a new technology, usually dampened by established supply chains, lag in infrastructure, including IT infrastructure and also IT security concerns for new technology. I'd like to submit Exhibit A as evidence of this. If you've spent long enough time on a factory floor, you have likely seen one of these, 3.5-inch floppy disk, not in use since probably Windows 95, but still available on today's factory floor. And when technology surpasses that, and we have much better technology to deal with something like data storage or data transfer, we still don't necessarily evolve. We evolve the devices to convert the floppy drive to USB. So this is my evidence submission for heavy industry being a fairly overdamped type curve, where we are generally fairly slow to new tech adoption. So to judge the feasibility of an application, to try and say critically damp that hype curve, to get to the ideal adoption as quickly as possible, as efficiently as possible, we should be very meticulously judging the feasibility of every potential application that is put in front of us. We do that by some key performance indicators, by some metrics that I've outlined on the screen here. The first one being fairly heavy, because it is judging what we are competing against, whether we are competing against an exorbitant cost, a long lead time, or even, say, the inability to create a part or some geometry, were it not for some of the enabling features or advantages of additive manufacturing. So in the traditional cost or lead time category, we have either an enabling or a replacing, so replacing even some exotic material, but also for some highly skilled and hard to staff workforce through moderate fabrication. We may be just replacing some moderate or complex fabrication that takes a couple of parts, or some welding or some piece parts that need to be ordered special and then fabricated, towards what I would say is the highest difficulty to replace with additive, which would be a commercial off-the-shelf or some generic component, generally not suitable for 3D printing because they are already fairly well optimized with the advantages of commercial industry, with the advantages of economies of scale. The second metric, which is specific to additive manufacturing when judging manufacturing feasibility, is the service temperature, whether the printed part is being used at room temperature, under slightly elevated temperatures, or I have the maximum metric result here being an oven cure, so an approximately 350 to 400 Fahrenheit oven cure. Followed by the geometric complexity, whether we are talking about needing to form a single surface fairly close to uniform surface normals, trying to get one specific form and not having the constraints of the rest of the part, the sides, the back side. It leaves a lot of geometry to cheat from if we can just maintain our focus on a single surface and the rest of the part is existing just to support a single surface or a single form factor. Moving on to 3 to 5-sided parts or 6-sided parts, say fully formed, fully encompassed geometries where the entire geometry needs to be very accurate because there are multiple sides of the part that are functional. Through to very intricate detail, so finished parts that have small details that maybe even can be judged by saying they have a resolution or detail that is tighter than the print resolution. So if we are printing with a 12 millimeter or a 1/2 inch wide bead of plastic and we need details drawn into the part that are much smaller than that maybe the print resolution doesn't support. A lot of applications in tooling applications, whether they be cure tools or vacuum hold fixtures, are requiring some vacuum integrity, whether that be none at all for more passive tools, to requiring at a minimum to be able to hold vacuum with a continuous pump, to needing a qualified hold at the high end where we have a very specific number of inches of mercury drop per 10 minutes without vacuum applied, so fully vacuum proof. And finally, dimensional tolerances, whether we're talking about specifically an artistic or a cosmetic application where the part needs to look good and maybe provide its purpose from a distance, not interact with other parts, through to a part that needs to fit together or replace a process such as a casting or a forging, where we're just replacing a normal fabrication process, to fully aerospace dimensional parts, where we're talking about a few 50 to 100 micron over a few meters cubed. So the old adage is when we want fast, cheap, high quality part, you really only get to pick 2 of those. So we're talking about basically at this highest difficulty level, the most difficult metric result in this category here. The old adage is we get to pick 2, either fast, cheap, or high quality. The slightly more engineering approach is to create a decision matrix out of this. Here we have a max score of 15 being the most difficult, Maybe some of these categories don't apply or are very enabling. Some of them might deserve a score of 0, but for these purposes, we're going to score between 5 and 15, where 15 will be the most difficult. And really, we are comparing, not necessarily drawing a hard score, but at the end, we'll look at multiple applications and see how they rate compared to each other. So let's get through some example projects. First to present is 2 projects in one. Is revolved around this nacelle fan cowl with a radius of approximately 1.5 meters shown here, and we are talking about both tooling for the yellow panel and the teal stringer forms. This is a project that we've done. This is a successful print within 1 week. This is actually done on a robotic platform at Ingersoll. And the first application related to this job, or tool printed related to this job, is a layup tool. So replacing the proof of concept or process development tooling before final engineering was approved or released to have a tool for room temperature layup. And in lieu of being able to stand at a podium and speak in front of everybody, I present myself as a speaker. I wanted to say hi to everyone here. So the fan cowl tool for panel layup is replacing fairly moderate fabrication at that size, some relatively dimensionally tight form factor that would need to be welded and then machined to final dimension at room temperature. A single surface that we have to care about where the back of the tool, the substructure, can be engineered to fit the printing process, not necessarily to fit the functional job of the tool. Not requiring any vacuum integrity, but requiring high dimensional accuracy to be able to judge the quality of the layup. This results in a score of 8. The second application for the same job is tooling plugs. So we printed a male version of that same panel tool to be used to produce carbon fiber tooling, CFRP tooling, for the production molds, the production layup, the production cure tools for that fan cowl panel, as well as the negative of the stringer tools. These jobs supporting the fan cowl project CFRP plugs are again requiring or replacing a moderate fabrication, now at an elevated service temperature from the tooling material cure temperature. Again, moderate geometric complexity, requiring at a minimum vacuum integrity to be continuous so that we can pull vacuum, even if a vacuum may need to be held with a continuous pump. And again, aerospace dimensional tolerances gives us a score of 11. Switching gears, there's another industry that might be interested in large format 3D printing. This project is scale testing for the marine industry. This part was printed in 2 pieces. You'll see a picture and a video of the print in a second, but here we see the pieces as they've, the split line has been machined. They've been assembled, both with pinned connection and bolted together, and then machined as an entire piece with the 5-axis milling head. Here we'll see a video of the parts being printed. You see them grow. This job was printed in 2 pieces. You see a third that we kept for ourselves the machine, the extruder had the throughput, the machine had the capacity, and while we were printing, we printed a third for our own testing and as a showpiece. This example you see is utilizing the 45-degree printing technology, where we're actually starting from the, call it, far bottom corner of a print and growing to the near top corner of a print, slicing the print at 45 degrees. So this, grouped into a category called the test tank model, is replacing moderate fabrication, being used at room temperature, a 3 to 5 sided part, so fully encompassed. There was not a lot of tightly toleranced features on, call it, the deck of the boat, though it was machined for fit and access points. But in reality, the form factor for hydrodynamic testing was a 5-sided part, not requiring vacuum integrity, and despite being a marine application, requiring aerospace dimensional tolerancing, also aerospace grade surface finish to get proper results from the hydrodynamic testing. Grouped together, we have smaller molds, both for carbon fiber and glass fiber vinyl ester for the automotive and marine industry. These are slightly smaller projects, easier to move and inspect by hand, oftentimes able to be laid up by hand or even sealed by hand. In this case, the differentiating factor is that we are usually replacing not a exotic metal weldment, less intricate fabrication, but more so a foam tooling block, a high density foam that is glued up or epoxied up into a certain stock shape and then machined. So there are different advantages and disadvantages to this family of applications. So in this case, we are replacing moderate fabrication, that it would still require a machine tool if we're coming from the tooling block family of replacing that as a traditional manufacturing method. At a slightly elevated service temperature, mainly seeing the exotherm of the epoxy cure process, or possibly a low temperature pre-cure for high temperature freestanding post-cure where the tool is not involved. With 3 to 5 sided geometric complexity, again, usually some form, some surface being on, call it the base plate or the tooling plate that is untouched. Not requiring vacuum integrity, again, because these smaller parts or for these industries can often be finished with a fairly intensive mold sealant. And then dimensional tolerances, depending on the application. In these applications, they were less intensive, so falling into category 2, slightly closer to fit and fabrication tolerances. Not that they didn't need to be machined, or not that they could be sort of eyeballed or tape measured, still requiring an NC machine, but more on the line of needed to be functional, but could be pushed into place at final assembly. Getting on to a much more intensive application, here we have a cure mold for the aerospace industry. In this case is a winglet layup tool. We have a winglet of a jet, and we have that aerospace form factor with a plethora of tooling ball locations, multiple scribe lines, some fairly intricate geometry when we get towards some of the tight curvatures in the mold. And you see it here being printed in the vertical format. So with a straight nozzle being printed directly as height off of the print bed. This is replacing moderate fabrication, needing to withstand an oven cure, AEROSPACE composite cure tools, a 3 to 5 sided part where we have the composite laminate that needs to escape the mold, so there's some opening. Needing to withstand or perform at the highest level of vacuum integrity, and again, AEROSPACE dimensional tolerances. This gets up there as far as stringent, as far as a very high demand application. Here we're showing a bridge girder mold. The application was for concrete casting. This is very large, 3D print, again printed at the 45-degree slicing, 23 foot long, and this is a concrete casting. We have a video showing the print in our development center in Rockford, and after the back wall is formed and until the end cap is put on, is a lot of repeat motion, basically the exact same layer again and again for the middle 2 days, let's call it. So these concrete forms are replacing precision carpentry. It's moderate fabrication happening at room temperature, still requiring machining for final form, still trying to get as close to near net even with the concrete casting process. Not requiring vacuum integrity. We can seal the mold otherwise manually, and not requiring the most stringent of dimensional tolerances. The final category involves two applications that were printed on a machine at the University of Maine that was commissioned over the last year. This is a slightly larger machine than our Rockford Development Center. This is about 6.5 meters between columns, 18 meters of length, and pretty enabling or important to 3D printing a 3-meter Z-axis stroke. So with this, we printed an example boat hull. This is a world record print with the world record Ingersoll printer, certified by Guinness. This is the object that was printed. The University of Maine has a test tank that they can fabricate waves, or manufacture waves and wind patterns above that. So it floated in their tank. We trailered it, attached a motor to it. This was a demonstration piece. This was a full final part, but used as a demonstration. Same with this demonstration piece that was a soldier shelter system. So for lightweight, rapidly deployable structures that can be mobile, here shown on the back of a truck, a standard shape on the outside, customizable for usage on the inside, printed as a demonstration for the United States Army Combat Capabilities Development Command. So these put into a category called structural demonstrations, where the part needs to function, but they are, in this phase, more so a demonstration. They are head turners. This gets a good score, so a low score in the traditional competition category, because they are serving their purpose specifically because they were 3D printed. They are enabling something, or they are replacing a traditional form of manufacture entirely, doing so very rapidly, and their purpose is to show what's possible. Being used at room temperature with varying degrees of geometric complexity, but oftentimes down the middle where we are utilizing, not pushing, but not violating the capabilities of geometries that can be 3D printed. Not requiring vacuum integrity, and the dimensional tolerances, again, can be varying between the artistic or cosmetic. Just needs to look good to maybe it needs to do something or at a minimum serve some functional purpose in category 2. So to recap all of these from start to finish here, we have sort of production trials, and the difference between production trials and tooling plugs is a significant score gap where the parts need to start performing at temperature and under vacuum. We have a group of slightly lower performing, so say easier to validate, higher feasibility in the marine molds and concrete forms. These still need to do a significant job, generally at room temperature, generally without a need for to pull vacuum. The highest scoring, most intensive application requires the most experience, attention to detail, first time right mentality, carbon fiber cure tools, which need to perform at high temperature, hold vacuum, and be dimensionally accurate. It's a plethora of hurdles to overcome there. And then finally, structural demonstrations, which if it's something that that will gain attention, that will expand the imagination, that will test the applications of large format 3D printing, but as still mainly purposed as a demonstration, that is ready to go with a low score, high feasibility for a good print job to select. Across all of these projects, we see that some common advantages and disadvantages of 3D printing. There's a group of pros and cons. Pros being that we have a rapid response to issues. We have a rapid response being able to make prototypes early and being able to produce late. So a lot of times, just-in-time production is not planned as just-in-time. It's happening as just-in-time production because it needs to. But it does allow the prototyping of aero surfaces or other tooling to be done before or maybe while there's still high risk of engineering change. It captures the entire manufacturing process in a digital process where small changes are easily repeated. So a small change to a part or a family of parts has been proven and tested, and we've printed one of them. It's very easy to make a small change and print it again without going back to say the drawing board for designing the process or proving out the materials. It allows for customized production. So like digital manufacturing allows, it allows customized production where a lot of unique parts or unique part numbers, maybe in the same family, can be printed for not a lot of added manufacturing cost and lead time. And at certain times, it enables geometry. I'll also talk about how it at certain times restricts geometry. There are only certain things that can and can't be printed. Some things can only be printed. Some things can't be printed at all. The cons is that currently we are material limited. We've talked about reinforced thermoplastics, and in large format reinforced thermoplastics, there are some strength to weight detractors. The durability for many processes is still to be tested. The parts often need to be post-processed, and we are producing in serial. This is not the parallel production of multiple parts in a multiple part injection molding die that a lot of times, at least on the desktop scale, 3D printing is expected to replace. And then the same way that additive enables design and production of some otherwise impossible geometries, there are manufacturing features that are easy for traditional manufacturing, but very difficult for additive. Near net shape fabrication and internal voids, that's exactly what additive manufacturing excels at, and is very difficult for traditional manufacturing, if not impossible. Versus some tight tolerance to flatness, very, very round holes, very high quality surface finish. These are easy for traditional manufacturing, and they're some of the highest hurdles to jump for additive manufacturing. So all in all, the additive manufacturing process enables rapid development. We have in-stock materials, we can make quick design iterations, we can do testing of partial prints, partial parts, scale them down very easily, and then scale them back up when the process is proven. And that's because it is a digital manufacturing process where the machine is doing the casting and the finishing. So this helps us jump that gap, that divide on the shop floor between we have a concept and we ran it through the computers, we've simulated it, it should work, to okay, we have something to play with. We've gotten something in front of the engineers on the shop floor. We have some tooling where we can actually start making a part. And it may not be as durable or as efficient as the long-standing production part to make 1,000 units, but it will help you iterate as quickly as possible. So a final poll now I'd like to ask very specifically to large format additive manufacturing for industry. Where are we? Where are we on this hype curve?
Thank you, Curtis. Yes, as you have already mentioned, please vote between tech trigger, inflated expectations, disillusioned, enlightenment, or stable productivity. Again, if I may ask, what results are you expecting on this one?
Sure. Yeah, I'm expecting. Again, I don't want to guide the results before they're in, but I am expecting, after specifically calling out large format additive manufacturing, maybe to see a little bit more dispersion towards enlightenment, or even some weighting towards the disillusioned, as I've highlighted both the advantages and disadvantages and how some of these applications are still progressing.
Thank you very much. Let's see the results. So 7.1% have voted tech trigger, 21.4% inflated expectations, 3.6% have voted disillusioned, 60.7% have voted enlightenment, and 7.1% stable productivity.
Great. Yeah, so I'd like to call out, where I think some of these applications fit. First, particularly talking about different markets. So to wrap it up, I'd like to say I think that some of the consumer products are still climbing towards the peak, so printing for the consumer. And we see what I'll say is ourselves, or at least the topic of this presentation, large format end use parts are maybe still progressing out of the peak, or still receiving a lot of hype. I think some structural components are still maturing, as a lot of applications are being formed out of the results of the just for show demonstrations. So a lot of the just for show demonstrations are weeding out what is good and what is bad for AM for end use parts or for structural parts. I believe that Cure tools still need to find their niche. I think it lies in leveraging the specific advantages of additive manufacturing that we've outlined, and that means custom geometry, requiring digital manufacturing, requiring a quick response time. And I think it will likely end up being geared more towards R&D and repair jobs. That large format tooling is grouped into all of that, structural components, feasibility demonstrations, room temperature tooling, cure tooling. But that rapid prototyping is where additive started. It's been around the longest. It's the longest run market for 3D printing. Specifically shown here is now these large format applications where we have structural components still receiving a lot of attention and as I said, being weeded out by the large format demonstrations. Cure tools requiring some leveraging still to be done, specifically based on their advantages. This may end up being particular to short-run jobs, R&D, maintenance and repair operations for composite skins, and that the maturity of cure tools needs to be facilitated by, or I would say even the maturity of all of these large format applications would need to be facilitated by a hardened production support system. So a shop floor that's familiar with the additive process and how to handle and deal with printed parts, and also a reliable control of the printing equipment in order to eliminate lost time and in order to have fewer failed prints, a more higher probability for first time right applications, so that additive can truly capitalize on its advantages of low cost and short lead time. With that, we can open it up for questions in the Q&A.
Thank you very much, Curtis. Just a reminder to the audience, in order to ask any questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click submit. But it looks like we've got some questions coming through already. The first question for today is, can they do tapered objects with MasterPrint technology?
I'll do my best to answer this. Maybe we can talk more. There's a contact us in the email. I'm not entirely sure what the question means by tapered objects. Definitely, we can print all types of free-form shapes with and without different support. So much depends on the specific geometry. Tapering the bead size is possible, but tapering a particular geometry, definitely any sort of cone shape or free-form shape, whether it's printed in the Z level or some of the 45-degree sliced examples are a little bit more enabling for parts that we're trying to eliminate a support structure.
Thank you very much. We have another question, which is, do you have any information on 3D print of parts for hydropower turbines?
We don't have any specific examples for hydropower. I would like to investigate more though as to exactly what we're trying to replace. With every application, again, I'd like to say, are we replacing a casting directly, a plug? Are we replacing a form tool, or are we trying to replace the final product? That's a pretty hard differentiator. Excuse me, whether we're trying to replace the final part or some tooling to support the job.
Thank you. Another question is, how easy are the printed parts to machine?
So that always depends on the geometry that we are machining. But if we're comparing a printed part to be to a part that would be an aluminum casting or a forging or some other form block of foam. In general, we can talk about the material as it is fiber reinforced makes a very neat chip. So as far as machining the material, it's fairly problem or stress-free to machine the part, and in general, say rule of thumb is about 25% the hardness or material toughness or horsepower draw when it boils down to it of machining aluminum.
Thank you very much. And another question, what software do you use to program the part and control the machine?
To program the part and control the machine, Ingersoll uses an Ingersoll software that's leveraged from our composite LAYUP software. So as 3D printing advances, the software is going to have to be apace and more being demanded to support complex geometries or out-of-plane slicing and working directly with engineering data. So Ingersoll uses a proprietary software that is controlling the process from part design or after the part is designed, is controlling the path planning through the post-processing and simulation, even following the manufacturing data to the shop floor and managing the job on the NC, so on the machine control.
Thank you very much. And last question that we will have time to cover today is, are you likely to incorporate printing, machining, and tape layup on the machine in one machine?
Yes, absolutely. And if we do that, from the machine design, the same way we incorporate, say, two different types of layup, tape layup, fiber placement, we can incorporate any number of modules to support the complete manufacturing process. What that really enables is the ability to make sure that the machine always has a job. So when we have a fully capable machining head on a print head on a layup machine, the machine itself in the factory will very rarely be in want of work.
Thank you very much. Just a reminder for the audience, your questions will be available to be answered at a later date. So that just leaves me to thank Curtis for what was a great presentation and to Ingersoll Machine Tools for sponsoring this session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye on the website just mentioned and follow us on Twitter at BR Webinars for daily updates. You can also join our LinkedIn group, Business Review Webinars. Thank you very much once again, and I hope you all have a nice day.